Okay, it's 9 o'clock. Let's get started. Good morning, everybody. Welcome to PyCon 2023 from my side. My name is Mike Müller, and I will be your tutorial instructor for this morning. So we're going to look at object-oriented programming in Python, how we do it and why we do it. First, I would like to start with a short introduction from my side that you know who's talking here for 3 hours, and then I want to get a little bit of an overview over your Python skills and expectations. So I've been a dedicated Python user since 1999, so I can always claim since the last millennium. So I started with the version 1.52, I still remember. Yeah, I bought my first book in April 1999. I don't have it anymore. I lent it to somebody and didn't get it back. I don't remember to whom. But this would be like a historical document because I started. And then I programmed pretty much on a daily basis, and it happened that in 2004 gave my first training. So, because I gave some lectures at university already, some other stuff, and so I can say, okay, why not give a Python training? And I gave a Python training. So the thing developed. 2006, I founded Python Academy, which is the logo here. And since 2010, I do this full-time. Currently, we have quite a few other trainers in Python Academy, so we are a team of trainers training Python, and we specialize in Python. And we do some tutorials like this, but also introduction to Python, advanced Python, a lot of scientific and data science topics, SQL alchemy, testing is a big topic, database programming in general, Python programming, high-performance programming with Python, and so on. Okay, that's about me. I would like to get a short overview about the people in the room. I just asked you how long you use Python, which is not a really good measure, but better than nothing. So please raise your hand if you program Python less than 1 year. Oh, that's like 20% or so. Between 1 and 3 years, so if you use Python on a more or less regular basis. Yeah, that's one more. Between 3 and 5. Also more than 5. And that's my minority. Okay, so kind of distribution, more people that don't use Python extensively long, which is kind of expected. Good. Let's go. I have a few slides, and then I explain a little bit how we're going to do it. I talk a little bit about the objectives. So the objective is here to learn the basics of object-oriented programming, and so we look at how to create a class. We look at the concept of inheritance, which is an important concept in object-oriented programming. We look at operator overloading or the special methods. So operator overloading is actually a little bit too narrow, we will see, but very often use this term. And the way we do it, we start with a procedural code. So I will give you a short procedural code, which is working already, and then we step-by-step convert it to a more object-oriented solution, see if it's getting better anyway. So if it's worth it to do, or how we do it, and then see how much it gets better, or if you like it better, or feels better, works better, whatever you think it's better. So we learn about the advantages and also maybe disadvantages. A few years ago here at PyCon, there are the talks like don't write classes, which is like the direct opposite to what I'm doing here. So disclaimer, I also teach a full day of functional programming in Python. So Python has some functional features, and I like them. And they are useful, and it very much depends on the task at hand. So Python supports multiple paradigms, some functional, the full selection of object-oriented features, and you can use them and you can combine them. So, and you learn some basic techniques of object-oriented design, how to design a program. So we only have 3 hours for the whole thing, including some exercises, so that cannot be like a multi-week design course, obviously. But I give you some basic things you understand that might be useful to design programs. Good. So we start with an example code. I will go to show you pretty soon. That works already. So we go through this example code, a few minutes that you understand. Hopefully it's not too difficult. I chose not just the hello world, yeah, that's too simple, but not a very complex thing where we spend 3 hours just trying to understand what the thing is doing. That's not going to work either. So we have to have some in between. It's still a toy example to some degree, but you will see you could make it way more complex very easily. Yeah? So if in real world things tend to become more complex. And then we convert it into object-oriented code, and we apply these principles when we do this. And hopefully this is useful, and you see how this works. A few words about this programming paradigms. If you go to Wikipedia, you find more like 70 or so different paradigms. There's very different kind of hierarchies and structures and stuff, and very different names. These are the main names you might see. So we have these big groups: imperative programming and declarative programming. By far, the most people do more or less imperative programming. Procedural programming, that's you write your function, you call your functions in the procedures, or object-oriented programming, but we look now. Declarative programming, the main example of declarative programming is functional programming. The others are very rare, so logical programming is only Prolog around, and I never used it, I have to say, I have no idea. And the other ones I have also not much idea, so they're also in this category, but they're even more rarer than the other paradigms. Good. So some people say it's all rubbish to do all these paradigms. I don't think so. It helps to a certain degree if you don't take it as a religion, say that has to be this paradigm. You can always combine it, but sometimes it helps to have some terminology to communicate what you want. So Python's generally pretty pragmatic. You want to get the thing done, and how you call it doesn't matter too much, but sometimes words and those definitions can be useful. Okay, object-oriented programming, there are different ways how you express it. My background is numerical modeling, that's why I always come with modeling here. So modeling, what is modeling? Modeling is having a simplified representation of the real world. We do modeling all the time. Yeah, so most of the sentences, if you count something 1, 2, 3, 4, that's a kind of modeling where you represent something with a number, but there's no number out there. It's just say three chairs. Yeah, but you say it's just 3, which is kind of if you want to say it's modeling already. Yeah, so it's simplified. And the important thing, we have an objective. A lot of people don't really start with it, but you say, okay, what do you want to achieve with a model? And then they have to simplify the model as much as possible to still achieve the objective, but don't make it simpler. Yeah? So you need to specify, and you also need to specify your assumptions. Yeah? So if you say, okay, we here on Earth, we can have the assumption we have Earth's gravity, which is usually a good assumption. If you take this model to space station, then it doesn't work anymore. Yeah. So, but very few people ever go to space station. For the big majority, the Earth's surface is fine, and assuming gravity is a good assumption most of the time. Yeah. So, but still, you have to write down your assumptions. The same goes for software. What are my assumptions? And very often, when you write them down, the problem becomes clearer already. So let's go to the example. I have an example. Driving electric cars. So 1.5 years ago, I switched from a combustion engine to electric car, and that's why I have this example driving an electric car. And driving an electric car is a bit different, as an assumption already. It's a bit different. So typically, when you have a gas car, you go to the gas station, you fill up, and then you go. It takes a few minutes, you pay, and you go. When you have an electric car, a big thing is the charging. So you need to charge your electric car to go from A to B. And this charging typically takes time. Depending on the type of a charger, you can get away with a few minutes. So like 20 minutes, you can get a decent charge if you have a fast charger. But it might also take multiple hours if you have a slow charger. So if you do just your home outlet, it might take several days. So it's just the weakest one. So there's a big range there. So this is the example here I would like to introduce, and these are the assumptions. So I wrote them down, and I wrote just down a few, and then after a while I looked at it and I did something. I said, I have more assumptions, and I added more and more. There's probably more you can add here. Yeah, so it's always assumptions. It's a good thing to have this assumption table there, because this is your world. Because we represent the real world in one way or the other in software, and then you write down your assumptions. So those cars just keep going. There's no other stops. They just stop for charging. they drive at a constant speed. So in real world, it's not realistic, obviously, but to make it simple, I'd say constant speed. You can always make it more difficult later. To have them accelerate and brake and stuff like this. Yeah. So the energy usage does not depend on the speed, which is even more unrealistic. Of course, if you drive faster, you need more. If you accelerate more, you need more. We take this out. It's just a constant rate. So, and then every car always starts with exact 80% battery capacity. So you have the battery charged up to 80% when you start there. And then as soon as you reach 20%, you stop for charging and you charge to 80. So typically, you don't want to unload to discharge your battery. You know this from this deep discharge is not good for the laptop and not good for the car battery because they're kind of similar. Yeah. So I'm not a battery expert, but in broad terms. And very often you also don't want to charge to 100% all the time. So that's go to 80. That's usually a recommendation. Also, this is usually the area where the charging is faster. Outside this area, it usually gets slower a bit. It slows down. It's not always linear. Good. So that's the assumption. And then the charging rate depends. So depends on the charging station you have, how much you can get out of here. Depends on your car, how much your car supplies. I talked to a guy here, the old car said, I cannot use this station. My car can only do 40 kilowatts. That's it. Yeah. The 150 kilowatt station is not useful for me. Yeah, and I have my car. I put it 150 kilowatt. It does about 110. It's the maximum you get out of it. So I guess if you're connected to a 300 kilowatt, it doesn't change a thing because it's a limiting factor. So there's no extra driving. Typically, when you go to this charging station, you might have to leave your route and go a few kilometers or miles somewhere and charge. We don't consider this one. And there probably are many, many more assumptions here. So that's a problem. So this is how it looks like. There's actually a result already of my run, but this gives you an assumption. This is one pattern for one car. We will see we use example data for cars. I computed them a little to make them a bit easier, and this is one of them, and it happens to Volkswagen, but it could be any Tesla, any kind of electric car. And you see here, this is the travel time, and this is the travel, and this is the distance, so we go 1,000 kilometers. So everything is metric here. So we go 1,000 kilometers, and we have a travel time in hours, and you see how this the distance is increasing, and I'm driving with a constant speed of 80 kilometers an hour. It's about 50 miles, yeah? So I go with a constant speed, and then I stop charging. The distance doesn't change anymore, so, but the time progresses, and I charge, and between these two red lines, I have the charging. That's what happens, charging time, you see? And it's always charging from 20 to 80%, all of them are the same width. This one is thinner because here I don't charge to 80%, I only charge as much as I need to reach my destination, and I still have 20% left. So this one has to be calculated backwards. Typically, but the car, it's always predicting when you drive, it all tells you when you reach a destination, you have so many percent left. It's changing a bit always because it's not constant, but they have a prediction in there. They take account your driving style and your last, I don't know how many trips you did and something like this. So they have some kind of prediction which is more sophisticated. This one, this is just everything is linear, which makes it easy. Okay, this is example. So now I switch to Jupyter Notebook. So this is a material, you have it already. I'm going to use Jupyter Notebook. Who of you is using Jupyter Lab, Jupyter Notebook? Something like this. So if you know how to use it, you can use it. If not, you don't have to. These examples work anywhere where Python works. You can just work from the terminal, no problem. You don't have to do anything special. They will work. But the notebook is great to demonstrate something. That's why I usually work with notebooks. Okay, let's look at the example. First, we have, maybe I make this bigger. Can you read this in the back in the room? It's big enough? A little bit bigger? Okay. Yeah, this screen is, compared to the room, not the biggest. So I'm creating new notebooks, and the notebooks have the advantage I can write text, and I can put the figures in, and I can load my code in here. So when you download this stuff, you will have this these two PDFs, and then we have the directory eCars, which has all these different versions, different versions of my program, different incarnations, and you have the data here. This is the data. These are not the original data. I have a long explanation where the data come from, so you can read through, but it's not of interest here. So I used them and modified them a little bit and took something out to make it easier to use. So the data is like this. That's how it looks like. You see this is not good because it's a this is so I have to open it. I say it's CSV, but that's not a good opening. So this is the data. Actually, I can load the data from the notebook. I do make a new notebook. I start with new notebooks. So you're encouraged to, if you can, type along or work along or just listen. We will do exercises. I have an exercise where you do something yourself. I will be here. You can ask me questions, but it's important that you're actually kind of more or less active. If I'm just always talking here and giving a long presentation, that's not too helpful. So the data first. So look at the data. So if I cd into this, I cd into the eCars directory. No, I'm there already. I'm there already, so I started there. Of course, I put the data, the notebook there, so which is not good, but there's, maybe close this. There, because it's not good to have the mix up there, so I cut it out. Mix up, put it in the. I want to put all the notebooks there. Okay. So now I can say ls, and I say cd eCars, and then you can look at the %less. I've forgotten already what the name is. ecars.cv, less ecars.cv. So these are the data I changed a bit, and you see in the top we do have a short JSON thing with a unit. So I don't know if it's a good format, but at least we see the units. So this is our table. So we have a brand, Tesla or whatever, a model S1 or X or something like this. Then kilowatt hours per 100 kilometers, which is usage. The battery size in kilowatt hours, and the charging rate the car supplies. And then here we do have the data, and these are the data of we're going to use. So in the end, we can really make instances of that's real data, 3 years old, so it's not the most current one, but it doesn't really matter too much. So you can just put in new data. I modified them a little bit. If you want to, I have an appendix where I go in great detail how to do this, but let's stick with it. So let's look at a procedural solution. I will go over, so you know already the problem is not that difficult mathematically, hopefully. So I wrote a solution that produces this picture. We look at it a few minutes so you understand the problem. You need to understand the domain to a certain degree, otherwise it's getting difficult to do this. So let's look at the procedural solution. And for this one, I can make a new notebook. And I save it. It asks me to change it. Procedural. Okay, procedural solution. And the first thing, if I go to the eCars subdirectory, I'm using a config file where I put the config option. So if I can load this here to execute it, config.py. So my configuration is a very simple Python dictionary. So if you want to get more fancy, you could have a different input format, but for simplicity, I just use a Python dictionary. Here, and I specify my world data, my model parameters, if you want. Like the charger we're using supplies a maximum rate of 100 kilowatt hours per hour. That's a rate per hour. I don't know what this new line here doing there. Jumped in. Then there's the 20% and 80% thing, we talked, and then the speed 80 kilometers an hour. it influences the time. The speed doesn't influence the usage of the energy, which is not realistic, as we said, but this is our configuration. So since we use them all the time, we just import it, and then everybody imports this one, we'll get the same configuration, so we can compare our modeling thing. Good. So this is the data, and then let's look at the first one, calc travel times. This is calc travel times without anything. This is a procedural solution, and I have a bunch of functions that do things. So I need a bunch of imports. And now we have different things. We have driving and charging. So driving is actually when I cover distance. So then I drive somewhere. So this is the first thing I implemented in the function, and I do charge. We can look at this. Then we can also calculate the charging amount, which is not always constant. And then we have something called the travel. The whole thing is a travel, which includes driving and charging. So that's the terminology I use here. There might be different terminology, but that's what I'm using here. It's important, otherwise, very often when you talk with people and somebody says travel, or other says driving, what is what? Yeah. So driving is actually the thing moving the car with a speed of 80 kilometers an hour, where travel is the whole travel from the A to B. Good. So that's what I do here. So we start here calculating travel time. So I do import my config. Yeah. So if it's not given here, so I make it optional. Otherwise, the config is given, and I just extract exactly the same thing for my config file. This is the data we just saw. Yeah. And we calculate these things. So now we translate this 20% and 80%, multiply it by the battery capacity to get the absolute number of this battery. Yeah. So this is 20 and 80%, and this is this here. And here I divided by 100 because I want it per 1 kilometer. Yeah, for 1 kilometer, so it's easier to calculate. So the maximum charging amount is 80 minus 20%. We don't have any distance traveled. The remaining distance is the target distance, 1,000 kilometer. The travel time is 0. The current charging amount is the 80%. And that's our assumption. And then what's affecting effective charging rate is the minimum of the charging rate of the car and the maximum rate of the charging station, which is provided here. So if the charger provides only 22 kilowatts, then we can only use 22 kilowatts. Yeah, that's typical. 32 or 11 kilowatts are typical sizes, at least in Europe. I'm not here, but it's maybe similar. Good. And then I do the driving. So this is the loop where I do the driving. This is a little bit algorithmic. So I do the drives. Here I drive, and I call the function drive, and I provide this parameter. The function drive does nothing else, but here see this is I get the target distance, which are still 1,000 kilometers in the beginning, yeah, and then the available battery by the kilometer per hour. So if I'm at the end, this target distance will be shorter and shorter as long as I travel, and if I only have 10 kilometers to drive, I don't have to charge to 80% because it will be less. So that's what it is. And then, of course, the drive time is the distance divided by the speed, and then return the distance in the drive time. So. And then the charging is also very easy. You give the charging how much you want to charge, the charging rate, and then the charging time is just the amount, the rate. So a little bit mathematics. So this is a little bit algorithmic. If you don't understand all the details, it doesn't matter. We have a solution that works, and we have these components. Yeah. So we have this travel, and then you have to be a little bit careful if you compare to something that you round it a little bit. Otherwise, you might get into that one is not equal to 0.99999 or things like this. You want to avoid these kind of things with something like this. And if you reached your destination, then you stop. The thing is done. I'm finished. Otherwise, I calculate the charge amount. Yeah, give it how much I need to drive, remaining distance, and the amount min charge kilometers per hour. Do my computations. The calc charge amount is this one here. Okay, how much do I need? The minimum charge plus this one, so the minimum charge has to stay there, 20%, and then the remaining distance by the kilometers, how much I need. And if it's more than the 80%, then I charge to 80%. If less, I charge to this thing. So that's why I take the minimum of this and this. Yeah. So this is everything you need to make this picture, and I put it into functions. And then I return this time, and then I drive all my cars. So I read in the data. Actually, we haven't looked at in the data section. We also have actually here. I've forgotten how to read the data. Very easy, just for completeness' sake. Read data. Yeah. So we ignore the CSV totally, the The JSON part's totally and just read the CSV, and we don't do anything special. We just read the file in with encoding UTF-8. We start at the data. We split by hand with the easiest thing that we can do. You can use all kind. If you know pandas, it's much easier, no? But just do it by hand and go through and split the arrows. And I do some conversion, so everything that can be converted to an integer will be converted to integer. Otherwise, I try float. If not, I keep it as a string. So very easy, good enough for our purposes. If you need a more fancier reader, use any kind of reader. So it's not about data processing, reading data in. This is just a thing, and I just have this. Here on the data is a list of lists, as you can see here. Every entry goes in there, and then you have it. Yeah, good. So this is our solution, and in the end, you can drive, yeah, and report travel times just prints out the travel times, and I want to have the guy who is the fastest first, and that's why I sort all my cars. And to do this, I would like to use the travel time here, and I use the item getter, which is a function that I import up here from the operator module. So this one is essentially going into my dictionary and extracts the keys. The key here, it's a function, and this function can be used by key. Who knows how this sorting with a key function works? Just a few people. So I need to explain. So if I think I have an example here, I can use it. I don't have to reinvent a new one. Yeah. So if I have a dictionary, with entries, A is 10 and B is 2 and C is 24. I would like to, and we have to make a colon here, and I would like to sort my dictionary and say, okay, I want to have the B as a first because this is the smallest number. Then I could go on and write my own function, get value if you want. So I put my dictionary in. Yeah, so actually I don't have a dictionary, I have a list with dictionaries here. So I have to make my thing more complex, so otherwise it doesn't make sense. So I have a list with dictionaries, and this one has this one, and I copy this whole thing, and now I want to sort it by one of these things. Yeah. So, and now I just use the value of B, and here I say this is 25, and this is 8. Now I would like to sort by B. So now I get my dictionary, and I just return my dictionary value B here. Yeah. This is a function, and now I can say sorted of my dictionary, of my list. Actually, I call it a list. It's a better name. And this function is okay. I put in my here, and I say key function is my sorting function. Yeah. Get value function. And now when I sort this, now you see this is the first, this is the second, the third, because what does happen? So if you add a print here, you see what Python is doing. So you add a print, and then you see when I call my function, Python hands in every element of my list, which happens to be a dictionary, to this helper function get value. And I retrieve the value for B, which will be used for sorting. So I create my search criteria, my search key. So if you can think of this is a function that creates a yellow sticky note where I write on what you want to use for sorting. So if you say we want to sort by first name, everybody writes a first name on a sticky note, puts it here. I sort you, and when I'm done, I take the sticky note away and you're in the right order. Yeah, because I certainly can't remember all your first names, but if I have a sticky note or name tag in this case, that would be useful. Yeah, I know the alphabet usually, so I can sort. So the same thing here, you write a helper function, and the item getter is doing exactly this. This is not unimportant because we want to use the sorting as an example for potential advantages of object-oriented programming. You can make your objects easier sortable. It's easier to sort them. You don't have to write this helper function here. Good. So that's what I'm doing here. And then I have a main function that reads the data, that drives all cars. So drive all cars just goes through all the cars, a list of cars, and then calculates the travel time of all of them. Yeah. So if I take this out, because now this wouldn't work. So if I take this out, yeah, and I load my file. Now I have my main function. Actually, it's easier to put it there, otherwise it's difficult. My main function, and now I just give it my eCars file, and then it prints out this car. So the Tesla Roadster here in this case is the one that needs 13 hours for the 1,000 kilometers, 13.7, the next one 30.78, and so on. So this is one is the shortest travel time with my assumptions. If you have different assumptions, yeah, then you might have a different result. You see, this battery capacity is very big, it's about 200 compared to the other ones. This is much smaller, but here this guy takes only 10 per 100 kilometers, and there it takes 20, which is really more realistic. Yeah, so it is always a combination how much you use, how big the battery is, and how fast you can charge. All these things matter. And then you can investigate. Yeah, so this is a procedural program. It works, and I can find out which car arrives first according to these simplified assumptions. Good. Any questions about it? So if you have questions, I'm supposed to repeat it because it's recorded, or if you would like, you can go to the microphone and talk to the microphone, then we have direct. Any question? Everything clear what we're doing so far? Good. It's supposed to be, it shouldn't be too difficult. So if it would be a lot of questions, then it would be too difficult because we assume we know our solution and the procedural solution, and we do something. So let's go and do something with objects. So we do something with objects. By the way, so we have 10:30, we will have a coffee break, 20 minutes or so, something like this. So you can get coffee outside and then we continue. Yeah? So let's go and do our first object-oriented solution. So, and for this one, we now take our existing solution and we don't really implement any new logic. You will see we use this, we don't do any new mathematics or anything. The end result is the same. Only the way we express things is different. That's important. That's what I want to show you. So if you don't want to, you can get away for a very long time without writing classes in Python. There's only a few cases where I need to write the class. So if you want to create your own exception, you have to inherit from exception and write the class. Yeah? And some libraries might make you to inherit from a class and write the class. Otherwise, you can most of the time get away with just writing functions. But writing your own classes can be useful, and that's why we want to look at here. Good. So typically a class. So you could have a class. So before we go there, you can have a class car. In our case, we will see it would be electrical car. And we have the class statement, and then we define a function, and the function inside the class is usually called a method. And then we have a self, and we have a value, and then I can say self value equals value. So this is a very typical pattern, if you want, for writing a class. Very often we have this init. This init is a special method. We will have a deeper look at special methods. They all have these patterns, 2 underscores, name 2 underscores. Very often called dunder methods, because you say 2 underscores, 2 underscores. You say dunder. Yeah, it's called a dunder method. And officially there are special methods. Some people call them magic matches, which is not actually correct because they're not that magic. Special methods that do something, and this is one you very often have. Most of the classes will have an init. You can write classes without an init, it's possible, but very often you want it because you want to initialize something. And here I could say def a method and then have myself, and then I increment something here. And then I say return self value plus increment. So it's not very useful, but shows the thing, what you can do here, increment And then I can make an instance of my car and give it a value. Yeah. So this is the first thing you can do with your car, and then you can say car.increment, and you get, so you can access the value attribute, and then you can say car.increment, car.method, and give it an increment this way around 100, and you do get something like this back. Good. This is the basic thing, and we see now we will look at my electric car, which is a bit more complex, but exactly the same thing. Okay, let's go to the directory eCars and import our file. We load our file, calculate our travel times, calc travel times, object on the way. So now you will see a lot of things. I took pretty much all the mathematics we have. There are not much changes, but I rearranged things, so the imports are the same. And I have my eCar. And you see, typically, per convention, class names are capitalized. And here I have multiple nouns. Here this electric, it's not a noun, it's an adjective, but we take it as a noun. And I shorten it to E, which is, everybody understands what the eCar is usually, so that's good enough. And eCar, that's why the E is capitalized and the C is capitalized for the car. We have electric car. We always use the most important thing for functions in classes is the docstring, so write a good docstring. So we have a docstring, and now you see I can get this configuration options. If you compare with our other solution, we'll see very often we move the same data around many times. Here we can use this one, and anybody knows what the underscore means? Yeah, it's internal usage. It's a pure convention, but the underscore means this is only supposed for internal use. In this case, internal use from inside the class. You can access it, but you're not supposed to do. When you write a test for your own class, then accessing is totally fine. When you use the library from somebody else, you shouldn't do this, because these things can change without notice. If you have another method or attribute, they cannot just change it. They have to have some procedure like a deprecation warning or something, and there has to be a documentation about this. And these things can also be undocumented, more or less, because they're for internal use. You see now I just take my configuration data, these numbers from here, and store them here inside the class, and this can be useful because now I can reuse them. So if you need data in many places, when you do it in a good function style, you always, a function should never change the outside world. You only get data in and get data out. And if you do this, then you can be pretty repetitive. If you need the same information at 3 functions, you have to hand it in as parameters, yeah, or arguments when you call it, again and again. Here in the class, you have something like a global scope. So when you write Python, you should never use the global statement. So if you use pylint, it will warn you, never use a global statement. Here, this is a global statement you can use, so to speak, and this is called the class variable, and this will be available over the whole class. See, now my init is doing quite a few things and is setting all this information. So there's a lot of setting. I set my brand, my model, kilometers, and all those kind of things, and I can pre-compute the things like this is my 20%, my 80%. All this computation we have done before in one of these functions. Yeah, there's nothing new here. So the travel time doesn't exist yet. I could introduce the travel time later, but it's a good style here to set the travel time to none. So the travel time is there as a name, but doesn't have a value yet. I didn't travel. You could set it to 0. It's possible. None is also possible. So this is a design decision. So it hasn't traveled yet, or maybe you could say if it's 0, maybe it started with charging. I'm not sure. So something like this. No, the travel time wouldn't be 0 anymore. So it could be the same thing. I decided for none, but 0 would be here potentially also a choice. Yeah. And you see, I have my drive in charge functions now moved inside the method, and they do exactly the same. I can reuse it. The only thing I hand in the self, we look at the self, and we see what happens here. Good. So and there's a few more things. Charging amount, it's the same mathematics here, nothing new. And the travel is also the same, but it's a bit shorter. So if you compare this travel function, this is a travel function, and you see the travel function needs to do all these things in the beginning, and this is what we do in the class on the top. So now we can better divide these things for this example. It's not always the case, maybe, but for this example, so I do all this static kind of getting things out here, and now my travel functions, which essentially mathematically exactly the same, becomes shorter and fits on a screen. Rule of thumb, a function should always fit on the screen. If it doesn't fit on the screen, it's potentially too long. So it doesn't mean you should use a 6 font and a 42-inch screen. That's not what I mean, but just a normal size font and screen should fit on there. So this is the same mathematics we do here, and then we have this in there. I'm reusing this function. This one I use in function. I don't write classes for these. So Python always allows to combine classes and functions, and you should always do this. And these things are potentially better done with functions. I didn't turn into classes. If you want to, you can. You can always turn everything into classes, but maybe it's not a good idea. In this case, I have it here, and I just travel. So we look at this in a moment. So I'm taking this out here, otherwise everything will be executed. So I'm executing this now. Everything in here, it's now in my notebook, and I can call all these functions because they're all executed. So the first one I have, I can read the data. Yeah. So read data, I can put in the file, and then I can read the data, and then I can have the data. So, and then we don't have to type anything in, we can use data. Data. Is read data, and we did this equals, yeah, this one. So I have my data, and then I can access data 0. So now how do I work with a class? The class is a blueprint for a new data type. So if you look at the type of this eCar, you will see this is a type. And if you look at the type of int, this is also a type. And if you look at the type of list, this is also a type. So int and lists are classes. So very often when I start with my beginner's class, I say, okay, I can use a function int to convert a string to an int. That's not correct. It's not a function. It's a class I instantiate. But it's a callable. So very often when you say function in Python, you mean a callable. That's an important thing. And instantiating a class and calling a function looks exactly the same. And in practice, you don't really care what kind of type you're using there. You care about the result. So very often Python doesn't really care about types. It cares about behavior. And that makes a lot of things much easier because it doesn't really matter what type this callable is, as long as it's callable. So as long as I can use this normal parentheses here, and it's giving me something back, I'm happy. Yeah. So that's why very often you don't know even if you use a class. A lot of beginners, when I type in a 1, I use a class because this is a literal 1 makes the instance of the class int. This object-oriented programming. So typing a 1 is object-oriented programming if you want. So suppose you make an instance of a class. Good. So now we have our car, and now we can instantiate our car. And you see, I can look at my eCar, and I can look at, with the question mark, at the help. So this is the same thing if you're in normal Python, type help, parentheses, putting in car, you see the help. And this help is obviously the signature of this init file. Yeah. So of course the class itself doesn't have anything, but this is these parameters here you want to put in, and I'm going to feed it with arguments. So if I have my Tesla, this is my Tesla here, this is data 0. My Tesla is my data 0. Yeah, and now you see I can feed them in. I can say now I make a new Tesla car. There's an instance, and I say it's my eCar. and I can say brand equals Tesla brand. So you can do something like this. So you can write this out, and you can type it in Tesla brand. You see, you have to type a bit. Model equals Tesla model, and so on. So I use the same names for some reason. So this also implies you can make it have a faster way of doing it. And then I say kilometers k per hour equals. So now getting pretty long. So this is one way of formatting it, putting every argument on one line. There are different styles of doing this, but this is something that works. And now I don't need to retype this, I can copy it. Yeah, so I can and instantiate my car, and I do the same thing here. Battery size equals this. You see, if you do like this, we use the same name. There's a shorter way of doing it. I can show you in a second, but I'd show you the long, tedious way first. Charging rate equals T charging rate. Yeah, so now I copy this. And now I have my, what's wrong, brand, I mistyped brand, yeah, so I didn't copy it. And now I have my Tesla, which looks like this. This is a standard representation. This can be nicer. We will do this. We will give our classes nicer representations. But now I can access my Tesla, and I can look at the brand, and I should say Tesla. Yeah. So you can look at all these properties. Anybody knows how we could make this thing a bit shorter? Yeah, you can use 2 stars for this. So if you want to say, let's say I make my Tesla 2, it's the same thing. I say Tesla 2 equals eCar, and I can say double star, for instance, double star, my T up here, and this Tesla, you can write Tesla like Tesla, then it's doing the same thing. So this one line is equivalent to this whole thing. That's what it's actually doing. This one unpacks the dictionary and feeds all the content in there. If you have a different string in there, it's not going to work. So the names, these names have to be exactly the same, otherwise it doesn't work. But this makes things easier, so you can instantiate it. So if you can guarantee this, and you want these names anyway, then you don't have to. And if you add another 2 parameters, it doesn't matter. As long as they have the same name, when they're in the dictionary, it would work. Yeah. So this is what we do. Now we have our eCar, and we can do something with the eCar. Let's look at our Tesla. So our Tesla now has a bunch of properties. Tesla. And if I say .tab here, then I do get suggestions. And you see there's the type I is an instance, and F is a function or a method. So we technically all these methods are functions. There's no difference. Yeah, but usually you call them methods when they're inside the class, and if they're standalone, they're called a function. But there's no technical difference. And now I can access all these. Max charging amount is so all these kind of things I computed in between I can access, and I can do this. This is an instance, and since I made a Tesla, obviously I can make as many instances as I like, but I can also look inside the Tesla. Now if you use another dunder, but this is not a dunder method, but a dunder attribute if you want, and this is a dictionary. This is how an instance stores the data. So this dunder dictionary is interesting to look at. When you program it, you might not want to modify it by hand because there might be some strange effects. Very often it works, but there are a few things that, like Python supports properties, they just look like attributes, but they're not stored in dictionaries because they have a different technology to work with. So it might not be exactly what you want to be careful, but looking at it is very interesting. You see now Python stores all this information, all these instance variables in this dictionary. Good message. If you know dictionaries, you know how this works. You know how this works, and you can access all these things. Okay, but I can also say Tesla, if I really like to, I can access these underscore things, these underscore things, and they are not stored in this dictionary, but still there. So usually when you say Tesla dot, then Python looks in this dictionary and looks for this string. And if it finds it, it gives you back the value. Yeah? If I say Tesla.brand, it gives me back the string Tesla. If I say underscore max charge, then it cannot find it here. And what does it do? It goes further and goes to the car, and I say car dot underscore dict, and the car itself also has a dictionary which looks a bit different. It doesn't say dictionary, it says mapping proxy, because this is read-only. You cannot directly write to it. You can directly modify the dict of an instance. This is something you have to think twice if you really want to do it. I wouldn't recommend modifying the dict of dictionary unless you have a good reason to do so. Like if you debug something and you want to introduce something to get a better output or so, that's totally fine. So for debugging, you can do pretty much everything. If you say, okay, I write some helpers to get some better information and throw it away. Otherwise, you might not want to do it. Here you cannot, because it's a mapping proxy. Otherwise, it's a dictionary. And you see all these things are here in the dictionary. So when you say instance dot, Python looks in the instance first, and if it cannot find it, it goes further to the class. Yeah. This has the advantage that I need to store this information here only once in the class. So this number is stored only once, and all instances share the same number. When you read, then you access the same number, and you don't have to store the same number 100,000 times if you have 100,000 cars. Yeah? This is important, saves bit memory, and also don't repeat yourself. If the information should be exactly the same, then it's probably better to have this information only in one place, not in 100,000 places. That might change independently. Good. So that's how it works. So you have attributes and these objects, the instance and the class, and you can work with these attributes when they're stored in here. Good. So now let's look at our car and do some traveling. So we can do some traveling. So if I have our Tesla car here, and I say travel time, then it gives me a none, which is not shown here. There's no travel time. It's not defined yet. Could be 0. Maybe you can change it to 0. Would be, I think, totally fine. And now I can say I drive, I travel my 1,000 kilometers to stay with our example. Then it's doing you don't see any output here, and then if you look at the travel time, now the travel time increased to this 13.8 hours. Should be exactly the same as the other example, hopefully. So this is this is not sorted. This is just I haven't sorted the cars yet. I just have one car that I read in. That's why it's not exact. It's not the same Tesla as we have when we sorted it. Good. Okay. Now the result is exactly the same. We have no new output. But the program is different. Everything is organized in a class and not only in functions, but we reused quite a bit of our functions and made them methods of our class. This is a totally fine approach, and you can do something like this. So if you want, you can also do a plot. So I have this plotting here. So if I have this, I can say from calc travel times this graph here, I import a different class. This is a graphed car. Yeah? graph car. And now I make my graph car, I'm lazy, just one, and I use the same thing, my t. Yeah, I have my graph car, and I can say travel 1,000 kilometers. And then this one now supports plotting. And if I say plot, so if I have matplotlib, so if you want to use a plot, actually you need matplotlib. Sorry, I didn't specify this one. And to suppress this output, you can semicolon. Now this would be the plot. So but the plot is not essential for the understanding object orientation. It's just you see this is the output, and you see that this Tesla, for instance, stops only 3 times for charging because it's a bit bigger battery compared to this Volkswagen, which stopped 5 times or something. Yeah? So this is something you can visualize directly. Now you can explore these objects step by step. So this is a different car. We don't need to look into plotting, how the plotting works. You can look at the code. I gave it to you. This is matplotlib. If you don't matplotlib, it's not of interest because it's not concerned with our object-oriented problem. Good. So now this is our program, and here you also have a helper function, show dix, and also the sorting. I can do the sorting the same. You see this. I can also sort by travel times, and I just put in, and also can use my attribute getter function, which is exactly the same as the function I wrote. It's just generating the function for me, and I can sort my cars to have the car with the shortest travel time first. So very similar to our solution before, but we have it in the class. Any questions? Everything clear? Yeah. So far the advantages don't seem to be the big. We can reorganize things a bit nicer. So we can have things that are in the class attributes, and we can have things that are in the instance. Yeah, and then therefore our travel function became a bit shorter because we could move something to a different place, and this is one advantage, at least for this application. Good. Let's come to the next topic, which would be inheritance. So we just can make new notebooks here. So then we have for each topic a new notebook. And we stop inheritance. Inheritance is one technology, if you want, or one technique in object-oriented programming that can make your life easier. Okay, let's have an example. So far, we said, okay, as soon as we reach 20%, charging starts, and when we're done, we keep driving. That's not how it works. Typically, you have to, if you go there, you have to stop, get out, you have to take your cable, put your cable in, then you have to take either a plastic card or some app, and then the app doesn't work, and they work around them. It might take a while to get connected. This time is not in here. This time is not in here. And we want to change our problem a little bit to include this time. So we want the most of it what we have anyway, so the driving, everything should be the same, only this little bit extra time to connect and disconnect from the charger should be included. So as an example, you have something and you want to modify it a little bit. And for this type of problem, inheritance can be a good tool. Yeah? The term inheritance comes from biology, so we will use the term parent and child, because they use this analogy of parent and child, and typically the child is very similar to the parent. In this case, you can have one parent here. Biologically, it's probably not so easy, but here you can have one parent. And in Python also allows to have 2 parents or 3 or 4, which is very uncommon, but possible. I wouldn't recommend to use it in Python, but you can. So we have this analogy. Of course, you say the child is very similar to the parent, but not exactly the same. It's a little bit different. It's not a clone, which would be 100% the same, but it's a bit different. And this principle can be used for inheritance. So let's look at our example where we consider this consider this charging connection, disconnection time, and we import, we load the file. I have to put the file name there. This must be the. Oh yeah, I don't start from the beginning, so I have to check myself how the file is named. Well, sometimes I don't know. So it's yeah, connection time. So pretty long name. So load travel time, connection time. So, and we need pretty much everything from our car, therefore we import our eCar here. That's what we just wrote. And now we do inheritance, and we write the parent, so the eCar is the parent, and this charger connection time eCar, which is a pretty long name. Yeah, you see this so-called camel case. This is a camel case because you always write the first letter of each noun, you capitalize them, and it looks like a camel. In nature, they only have two, but here you can have as many humps as you like. See, and then here I introduce the charge connection time. There are many ways how to do this. I use a class variable here again, so put something the classes will be available, and I say, okay, it takes about 6 minutes to do the whole thing. Yeah? And I lump both of them together, connecting, disconnecting, which is kind of reasonable because you have to find your app, and then you have different charging providers, and you have the wrong app, and so on. Yeah. So then you have this extra, and now you see I don't implement anything. I do get everything from my parent. So the child gets everything from the parent for free, and then I override the charge. Yeah. This charge method, I re-implement the charge method, and now this class, the child class, charge is a little bit different than the parent class. And the difference is very small. It still wants to do the same thing as the parent, and that's why you use super. What does super mean? Yeah, so there's another analogy. Sometimes the parent would be super and the child would be sub. So it is a different terminology. So and this means, please bring me my parent. In this case, this is very obvious. It can only be eCar. There might be more complicated cases when you have a deeper inheritance hierarchy. Here we only have parent-child relationship, but I could be a parent and a grandparent and a great-grandparent and so on. And there could be even, Python supports multiple inheritance, there could be two classes in there, which is not the common, but possible. And then you would have your ancestors from the mother side and from the father side, and then it can be pretty complicated. And sometimes strange things happen you don't anticipate, and the super is doing the right thing. In this case, it just brings eCar, and I call charge battery from the eCar. So if we go back to this solution, this would be, so we call this charge. It's not much. So I could easily copy these lines. This is just one line, essentially. This is just one line. But still, this is just one line. If you copy this line and don't change it, then you might think, do I have to do this? Is this maybe this an easier way? Because if you find a problem here and you fix this problem here, then you have to go to this other eCar also and fix it also. Yeah, and then you fix it in 3 places. Forget place number 4. That's not going to work for long. Yeah? Don't repeat yourself. Just try to do it in one place whenever possible. Yeah, question?
So in terms of the grandparents, would you layer the super method or
The question was a parameter layer. What does it mean, layer? Layers of parameters?
say we're not inheriting from the parent, but from the grandparent?
Yeah, so this one, we look at, this is what's called the method resolution. We look at it in a second. I make an instance. I'll show you how this works. Typically, you inherit from the parent. If you want to skip the parent, go to the grandparent, it gets a bit more difficult because you have to know who the grandparent is. But very often, the parent uses a super from the grandparent. This is a very common thing, that you have multiple supers, and the supers always goes up. It doesn't have to be like this, but it's very, very common. Yeah? You can also override the method and don't use super if you don't need any function. If you do something totally different, that's also fine. Yeah? So let's look how the super comes about, how this works. So again, I make in this case, I take this out here. So we can run this also from the command line. So I make a new car. So for this, I need to duplicate a bit of code because I made a new notebook. So I have to copy something like this. Yeah, of course I need to get my data in. Yeah, so I read my data, and the data is not defined. Good. So I have my data, and now I make my chargeable connection car, which I give this great name C here, and then I say, okay, make this car, and I can now feed in again starter data 0, which would be my Tesla. Yeah. So I have this car, and now this would be an instance. But the main thing actually is if you look at the MRO. What's the MRO? So if you don't know what it is, just look at the help. So of course, if you use this, say help. So in the notebook, I use a question mark, but the Python help is also the same. So if you look at it, say return types method resolution order. So the method resolution order. Then you say instance dot something. Then it looks in the instance and then goes to the class. And if it cannot find it in the class, it goes to the next in line. The next in line is the one in the method resolution order. And you can see here our charger connection time inherits from eCar, which inherits from object. Everything always inherits from object. Yeah? That's my sentence. I don't know how many thousand times I said everything is an object in Python because I repeated many times in each training. And this is the proof. You see the object is always the ancestor of everything. Everything inherits from object. Yeah, so if you say is instance object, it always works. There's no problem there. So you always have an object instance here, and the super does nothing else but uses this one and goes along this method resolution order until it finds a method. So if the parent doesn't have, maybe your question, if the parent doesn't have it done.charge, it will go to the grandparent because it looks in the parent and the parent doesn't provide it, it goes to the next. And in the very end, it will ask object for something. Yeah. This is also the reason why this output, this is called representation, looks like this. This representation comes from object. We will look later on how we can make our own representation. So object brings quite a few standard things with it. If you don't implement it, we get the standard ones. So this, you see now, this is a very short class, does exactly the same as eCar and does a little bit different. And this is nice because now you can go step by step and explain. For me, because I can pretty much focus on what changes. I don't have to copy the whole code or change all these functions. Yeah, if you do this with a charge function, you would need to write a new function that could call the function. You could do the same thing, but here you have a kind of a standardized way. That's inheritance, and everybody expects that something like this happens. When you write functions, you have to make it really clear that this function is called the other function and so on. Yeah? So, good. Inheritance is a concept that exists in Python, in object-oriented programming, and of course also in Python for quite a while, and you can do a few things with it. Good. Any questions about this? Everything clear? Good. So let's continue. Let's come to operator overloading. So I make a new notebook. And I call this overloading, operator overloading. So as an example, if I have two lists, I have two simple lists, and now I can say list 1 plus list2 and this works. Typically the plus is something for mathematics, for numbers, but in Python you can use a plus for lists, you can use a plus for strings. So how does it work? When you use a plus, actually in the background, Python is using the add function here, this add, this special method, this standard add, and I throw in this L2, put in the L2, and I get the same effect. In fact, if you have a number, the same thing happens. So you say number plus 5, I do get this one, and I can say number add plus 5, and I do get the 15. The same thing as adding it here. So whenever you use the plus, Python is looking for this standard add in your class. If it doesn't have it, it goes to the parent class if it exists and searches for it. It's not there by default, so object doesn't have an add, so that's why this one would fail. So this object doesn't support the add. So if you want to know more about it, you can go to the Python help. So this help opens just exactly the same Python documentation. And if I type in add, which I did before, obviously, then it jumps to object add, and then you will see there's many, many more. You see, this is a section emulating numeric types, and this one provides pretty much all numeric operations. Add, sub, minus, multiplication, and so on. The signs are explained here, not there, but you can read them up. So everything you can do with numbers, you have an add, and there's more, there's an R-add. So if the left partner doesn't have an add, it goes to the right partner, the second partner looks for the R-add for this partner. And then there's an I-add, which would be plus equals, yeah? Plus equals, minus equals, and so on. And a bunch of more, like a negative sign in front of the number could turn something. You can turn something in a complex int and float number, which doesn't make a lot of sense with a car, but you can do it with numbers, yeah? So this would be very useful. You can implement your own rounding. And this is not connected to an operator, like plus, minus, and so on, but to a built-in function. So the operator overloading is a little bit too narrow. These special methods do a bit more, yeah, because also this same here, these are complex int and float are not operators, but you type in complex int and float, and when you type this function in, or this name in, then Python is looking for the standard method of this object and applies it. Yeah? Same goes for len. So there's many of these, so if you want to, you can look through. There's more of these ones. This contains would be the in. So whenever you use, say, x in list, then if your object has a contains, it uses contains. You will see if it doesn't contains, there are some other fallbacks that it's also using for the same purpose. Yeah? The reversed, which should return iterator. So you have to read up a little bit how this works, and you can override a lot of these things, get item, set item, things, a lot of different syntax. Here you see this would be the set item, get item things. This explained, you have to read through if you want to implement some of them. You can also make your instance callable, for instance. So we learned that classes are callable and functions are callable, and you can make your own instances also callable by implementing the standard call method. The most interesting ones actually are to go up a little bit. They are top here, the comparison ones. So bool, you can make you can say here, my car is true or false. What does it mean? You could implement something like this, but the interesting ones are the 6. These are the comparison ones. Yeah, less than, less equal, equal, not equal, greater than, greater, equal, and then you can make your cars comparable. And that's what we want to do now. So that's what we want to do now. And I probably need to close some of those tabs, otherwise I can't see anymore which one is which. So close inheritance tab. So I have an example where we do this. So we improve this comparing. So we don't need to specify this key function anymore by improving our class a little bit. So I load this comparable car. So we can compare it. So, and again, I use the concept of inheritance. You don't have to combine them, but it makes it easier because I want to focus on it. So you see, I inherit from eCar already. We did this just now. And then I override this LT function, less than. And this is enough to make them comparable. The documentation says you might want to also have the equal implemented, but just to sort them, for sorting, this less than is good enough. And here we provide the same information that we would have used with this special key function. So we take the travel time. So the car with a shorter travel time will come first. That's what it says here. And now I move this comparison from a helper function that I have to apply from outside into the object. So the object is active to some degree. It can do something. So always, the object doesn't do anything, but you can think about the object is doing something, and this analogy makes sense. And now my sorting is easier. You see, the sorted now doesn't need this key parameter anymore. I can sort it directly and have the same output. So if I can run this here, which tells me this is not there because I changed the directory. And then you see now this is exactly the same output as before, but I don't have to specify a special key function here because I move the same, conceptually the same thing into the object itself. So the object knows what to do. I don't have to tell from outside what to do with the object. So if everything goes right, this would be an advantage that the object knows what to do and you just do something and it behaves accordingly, and you don't have to tell from outside with a function how to do it. And now we make it comparable, and you could override many, many more of the special methods if they make sense. Yeah, if it makes sense, you can override them, and you can improve your car. Good. And that's what we want to do now, because if you look at this e-car, so if you have our Tesla here, if I type in Tesla, you get this output. This is a representation. So Python has two built-in functions, representation. This looks like this, and there's str, which for many objects gives you the same output. Not all of them. Yeah. So this is exactly the same. If I say representation of a string, then it looks like this. Where if you say string from a string, then it looks a bit different. So there's a slight difference here, how things look like. Because a string is just a string, and this is just a string that represents a string, so a double string. That's why you have this double and single quotes here. And the thing is, if you run this through this is just the same source code. If I run this representation through a val, which takes a piece of string and evaluates it as Python code, then you should get back a string. That's the whole thing about it. Yeah, that's if it's possible. It's not always possible, but if it's possible, then the representation should. So if you do this with this car, it doesn't work. Yeah? But here it just shows you this is a standard representation of a class. It gives you the class name, which lives in main, which is my notebook, and this is an ID. So this is a hexadecimally decimally formed number of when you use ID. Yeah. So if I say ID from Tesla. ID from Tesla, and I convert it into a hexadecimal form, then it should, this does work, yeah, so it should give me the same. Yeah, so if you look at the number, that's the same number. Yeah, that's actually what it puts in. The ID is unique, yeah? That's the whole purpose of an ID, and then you can distinguish your instance of a class. The IDs can be reused. It's like you have a license plate from a car. If the car doesn't exist anymore, then somebody else can get the same license plate later on. Similar here. So it can happen. It's not very common, but it's totally possible that this one you can do. So make our car representable then. So I load my representable car and calc Why doesn't it load? So typically it should give me, okay, copy it in. So sometimes it doesn't like me. So and now I override this representation function, and now I can give it a richer representation. And this is up to me what I'm doing. You see, I have to return a string here, and that's what I'm doing. This, how you come up with a string is up to you, but it should look nice, and that's what I'm doing here. And I'm just using an f string to return a string. So now you have to give it a little bit more thought to make it reusable. So I could just say, okay, I take this name, represent the car, and return it. So let's run this one. So I can now, if I run the whole thing, I get an error message because I have the wrong directory. So if I run the whole thing, you see now, it doesn't look nice because I would need to, I have to put a print. What did I do here? Because I run it from the command line, I look good. Let's just use a print. Yeah, yes, choose a print, don't use a pretty print. So I have to change this, that looks better. So now you see I have a representable car, and this car looks like this. So this looks exactly this one. If you type this in, you will get the instance of the car. So now this is a bit more involved. To get there, you see I use a f string which generates a string, and then I do a little bit here, and I make it just list all this, because I have so many attributes, I just have a list of the attributes I like, and I use some formatting here to format them one after the other. I don't write it out by hand, I just format it. So, okay, go here, have a new line, the indent, which is 4 spaces, so add a 4 space and join these things here, and I go in this attribute, as I use get attribute, self attribute name. So go automatically into the instance and retrieve the attribute names here, and get these attributes for all these names here, and I can put them in automatically. When for this one gives me the value, because if I print this out, you see this is the names I provide, but this value is an instance information which I need to get out, and this get attribute does it automatically, and this get attribute does the same thing as self.attribute. And then I use here the representation of the object, and the producer. So that's a bit more involved, obviously. And then I also need to, anybody knows why I do this long thing here? What does it mean? Self-class, self-name. So this is representable car. So if you, this produces this representable car. So I could have just copied in a representable car. Why is it not a good idea to copy in a representable car as a string here? Any idea? Yeah? Namespace? No, this one in this case just gives, this one just copies this thing as a string directly in there. Yeah. Yeah, when you change the name of the class later, or when you do inheritance. So if you inherit from this class and you don't specify a representation, then Python says, okay, I don't have a representation, I take it from my parent, going up the method resolution order, and then it takes this one from the parent, and then all of a sudden my class with a different name says it's a representable car, which is not the case. It's lying about it. This can happen, yeah, and this might not be obvious. If you don't test for this, you don't see it. Yeah. So this, if you use inheritance, you should think about making your code inheritance proof. And this is not that easy. You have to think a little bit ahead what can happen. So if I write the class and give my module with a class to somebody else can inherit from my class. I cannot really prevent it. I'm not aware that I don't want to be inherited from. And then they can do all kinds of things. And then you should actually, you need to more or less factor in this use case that somebody's inheriting from you and what's going to happen if this is a child class or not my own class. It still doesn't work the same way I like it to work. Yeah? So this could be a problem. And so this representation thing is a bit more involved. I want to show you can do this, and then you get a nice representation here. And if you do this in the notebook, you can get even a little bit more. So if I say now, do I have my data here? Yeah. So if I say my representable car, look at the time, or is it representable car, R is a representable car. My data, level start data 0, which is my first car I'm reading in. So I have my car, and if I do this here, you see, now this looks different. This is colorful. This is colorful, which I produced because it's just a string. But if you're in a notebook, you can add another not so special method, but notebook special method, which just has one underscore on the beginning and end, is representation HTML, and you can generate HTML, which can be useful. So if you work in a notebook and you use pandas, then you always get this nice HTML table. Yeah. And here you can do it yourself. And this one, I don't do the work myself. I just use Pigments, which is a Python module. So if you want to run this, then you need Pigments, but it's not essential for the object orientation. And then this is plain Pigments. So this is if you go to the help page on the very first page, this is plain Pigment thing. How do I format, make everything nice, colorful, syntax highlighting. So there's nothing special. I don't have to write any single new line. And now I can have syntax highlighting. If you want, you can make your own HTML by hand and generate HTML with CSS, whatever you like. Yeah. Could be useful, and this happens in the notebook. If you do this in command line, you see this text without anything. Yeah. If you do it in, so if I say print R, which now this print R would use the representation, and that's the same thing, but you don't see the syntax highlighting. There's no colors in this case. Yeah. Can be useful making your object representable, because this representation is used when you debug. When you see an error message, you see the representation. And if you just see this is one instance of this car with ID, maybe it's not the best information. If you say this is this type of car with all this information, maybe it's much more useful because you say, yeah, okay, this value is 0. This could be the problem. This is what you can do. You can make your car representable. Good. Any questions about these special methods? Python offers many of them. If you go to the help, it's like 150. You never ever need all of them. There's many of them very special, very deep. Some of them are very common, like this add one for the plus, the comparison operators, the representation. Yeah, there's a second one that's called the str, which you could also implement. If the str is not implemented, it will fall back to representation. So since I don't have a str here, bundle str, it will fall back to the representation and uses this information from the representation. Now we make our object more expressible, and we move some functionality we had to supply from outside, like for the sorting inside the object. So the object can do more itself and move it inside the object. This can be an advantage if you create objects. Yeah? Okay, nobody does it, it's just see faces. I don't know if you don't understand. We have break. Feel free to ask me in the break if there's anything. So it's 10:30, it's 1 minute. So let's say 20 minutes, is this okay? Yeah, so 20 minutes, so we continue here, break till it's 10:50, 10:30 now, 10:50, and then we continue with our travel into object on land. Okay, we have 1 more minute. I don't have seconds here, but about 1 more minute. So please come back in if you're outside, if you can hear me. We would like to continue, so we have a lot of ground to cover. That's why we don't want to lose time. So it's 50 now. So first I would like to address a few questions during the break. A few people approached me, for instance, about the notebook. So all these notebooks I developed, I will share with you, because they have something, they have questions, answers in there. So I will take everything I have, notebooks. I also do have a solutions document, a PDF, and I put everything into the zip file and upload it again, so you can download the same zip file, and that includes all the stuff. So there's no new link. Give me an hour or so to do this. If I forget, just shoot me an email, tell if you've forgotten to do this. Then I send you, then I do it, just upload it. Yeah? A few other questions about these notebooks. People might not be familiar with a notebook, so last year I gave a whole tutorial about the notebooks. You can do way more than I show you. So these are kind of, you just mentioned the term prototyping. It's good for prototyping, for trying things out. As soon as you get more serious, move it to a file. So, because they have also disadvantages if you don't want to implement big classes. All my classes are on files, I just import them. I just show them to you here, but when you do something more serious, use your Visual Studio Code, PyCharm, all these nice tools you have, we can always combine it. There are some limited to reload options, so when you change the source code, imported function will be reloaded automatically. There are some caveats, it's not always working, but to most of the degrees it works, and you can combine. So notebooks are a great tool, but as always, you have to use the right tool for the right purpose. People complain this doesn't work. This is because you use users in the wrong way, then it doesn't work. Yeah? So you have to be aware of the disadvantages or the shortcomings or assumptions, as we stated them, then things become clear. A few more other things about inheritance. There was a question about inheritance and composition. So there's different approaches. So I don't really cover composition here, which I could, but the time is limited. So inheritance is usually a relationship. So an e-car is a car. So if I would have a car, I could inherit my e-car from a car because it's still a car. The composition is more has a relationship. So like a car has wheels. The wheel shouldn't inherit from car. A wheel belongs to a car. So that's a simple example, but these things are there. Also in Python, you can actually do a different approach. It's called wrapping, which I call wrapping. So instead of do inheritance, you have a class that uses an instance of other class as a proxy. You always delegate the work to this class. Because when you do inheritance, you always get everything from your parents. You don't have a choice. You either get everything or nothing. You cannot just say, I just want this method or this method. If you don't want to, you have to override the method. So you implement the method when you raise a not implemented error. That's what I call blacklisting. So if you do inheritance, you get everything. If you don't want to, you have to explicitly say, I don't like this, I don't like this, I don't like this. Yeah, and you have to be inclusive. It's like this can be difficult because you might not know, but you get everything if you're not aware that you get all these methods for some reason, because you get everything from all your ancestors there. So if you do GUI programming, so this is also a good example. If you write a graphical user interface, all the modern ones have classes, hundreds of classes, and each class has hundreds of methods because they have very deep inheritance hierarchy with a lot of, you get a lot of methods from a lot of widgets. In this case, most of the time it is designed like this, but it's kind of difficult if you have a class with 350 methods. How are you going to work with it? Yeah? So this could be a little bit overwhelming if it is so big. And this wrapping, you can do whitelisting. You can explicitly state, I want this and this and this, and everything else won't work. So whitelisting can be easier. This is a different approach. But you can do more things in Python. Inheritance can be great. A prime example of inheritance is exceptions. So if you go to the Python help, when you type in, so this also, let's keep this open, I make another help because I want to show this also. There was also a question. So if you go to the Python reference, when you say something like zero division exception or some kind of exception, you will go to the exception page. So if you go to exception page, and the very bottom of the exception page, that's a help page about exceptions in the Python standard library or Python standard help, then you have an exception hierarchy. And this is the prime example for inheritance because all exceptions do exactly the same. You don't want this exception to do this and this. They should do exactly the same. The only difference is the cause, why the exception is raised, and the cause is shown in the name of the class. Class names, camel case, yeah. This is a good example because all exceptions do exactly the same. They generate the traceback information, all the things. Only why they are raised or why they happen is different. Yeah? Inheritance makes a lot of sense. When you can write down your problem, you have nice boxes and arrows, and they assemble in a nice hierarchy that indicates that then inheritance can be a good solution. If all the boxes and arrows go like this, when they don't form a nice hierarchy, then inheritance might not be the best solution. Yeah? All those technologies can work against you if you apply them in the wrong way, because then they do a lot of things you don't want. Then you might heard the term, you work against the framework. So a framework gives you very nice tools to solve a certain type of problem, but if you have a different problem, and it's different enough from the framework, then you work against the framework. And it's the same thing with programming. So if your program doesn't lend itself to the thing, then maybe not use inheritance. Yeah? This is something that might not be so clear at the beginning, it turns out, when you work on it over time, I realize, oh, maybe not the best thing. Okay, about this less then. So here, the func tool modules in Python has a class decorator called total ordering. So we don't cover class decorators here, but this is a thing you put there and then it happens. So that's all you need to know here. And here you only implement equal and less then. And this total ordering decorator implements the other 6 of these comparison functions. You don't have to implement them with some rules. Yeah. Less than the opposite is greater than. That's easy, yeah? So just turn this around. And then you don't have to do this, and you would have all of these 4 methods working if you want to use your objects with those operators. So typing in these operators as an operator, then it would work. Yeah? So there's quite a few helpers here and there, which some of them I mentioned in the PDF, but I probably haven't mentioned it here. Good. Let's continue. One more thing about so I call this second constructor, even though it's not a constructor. Python has something called class methods. Anybody knows what the class method is? So if you have a class A, then you have a normal method, and when you have a normal method, you have the self as the first argument. What does the self mean? What's the self good for? What's the self? Yeah, the self is a placeholder for the instance, because these are functions in the first argument of the instance. I can explain this. So I don't, or just say return 42. So, and then I have a class method, and to have a class method, in order to have a class method, I need to have a decorator. So I need to decorate this one with a class method. So a decorator is doing something with my method, changes the method. You can implement decorators yourself, but this would take another 3 hours to explain all the things. So we don't do this. That's why I have this. So let's assume we have an init. Something like this, yeah? So and now I have it's very often called from A. I call it from A. And then here I get CLS. So in CLS, this is just, these names self and CLS are just conventions. They are not fixed. They're turned into blue syntax because they have a very special meaning, but they're not fixed. You can use any kind of word there, but this is very strong convention. You use self, and CLS stands for class. Back in the day, some people spelled class with a K or something like this, but that's not common anymore. So now I have this this one, and I just say I return a new instance of this class by using class and supplying this other a, the instance a, when I say a.value. So this makes a class from the other class. That's a very common, typical application of a class method. So a normal method takes the instance as an attribute. So if I make an instance of my class A, yeah, then I can say, which I have to provide a value, otherwise this work, and yeah, and I mistyped the value. So I can always fix it here. Go back in history. So A is this, and now I can say a method, and a method returns a 10. If I say capital S, a method, then it tells me, oh no, you're missing something. There's one, you forgot the self. You forgot the self. And the self has to be a special kind of argument. It has to be instance of the class. If I put the instance in, now this is doing exactly the same as this. Yeah, because the a method is a function, just a normal function, nothing special, just a function that happened to be inside the class, and the first argument is the self. And here, this method is a bound method. So it is bound. It's bound to what? It's bound to the instance. Therefore, you cannot, because the a is in front of the a dot method, then the a is consumed, the lowercase a is consumed already, then you don't supply this argument anymore. That's the whole thing. The method bounding is complex using descriptors and so on, but we don't have to be concerned about how it actually works. We just know that it works. Yeah. So if you want to, you can say a class in first is just a collection of functions that belong together somehow, and I have a bit more structured way to put them together. That's one approach if you want to. Yeah. And then they have a global namespace, and this global namespace is handed over with self. So the globals you don't want when you write functions, you use all the time when you write classes. So if you have some information that needs to survive multiple function calls somehow as a global, then probably a class is a good approach. Actually, I would recommend to use a class instead of global. Now, the global keyword, you should never ever use a global keyword. And if you don't do this, then probably you would need, if you want to do the same thing, you would need to use classes. Yeah? So this is a second constructor. Now we have this example here. And this one is what's the name? From class, flexible. Yeah, flexible. I call it flexible. So usually I have this. Yeah, so I have a class method. When you see now, this follows the same pattern as the class method. First is the class, and now I instantiate the class. And this is in this case, of course, is explicit flexible car here, which I can create with this. If somebody inherits from this class, this handed-in class will be the current class, not this class, but the child that's inheriting. Yeah. So now it just make an instance of this class which is handed in, and I now say, okay, brand is the instance.brand, model is the instance, and so on. I don't have to write this out. I can make it. It's kind of a copy, more or less. Yeah. And from something is very common. Anybody used pandas? Pandas, you can make a data frame from a dictionary, from all kind of stuff. They're very similar. So this is a typical name from something. And then you have a class method. And this would be explicit, so I specify everything by hand. But if you're too lazy, you can go a little bit deeper into introspection, and I use introspection module, and instead of writing this out, I use inspect up there, yeah, and the inspect gives me the signature of the init, and then I can get the parameters out, and I remove the self, and I do the same thing. This one took me a while to get there, yeah, so you don't write this just in half a minute, it takes a little bit, but this is exactly the same, but if now the class gets 3 more attributes in the init, or some more parameters in it, they would be automatically there. So this and this in this case is equivalent. No, this goes automatically, and all this, everything just inspects the init of the class and gets all this. These are the parameters of the init, yeah, from my parent class, of course. And then I just have the massage gem, I have to take the self out because I don't want to provide the self, and then I can do the same thing. And now I have the option to create a class from an existing class. So this would be a second constructor. If you want them, you will see this quite a bit. It's typically called from, and this is one example where I can use a class method, which can be useful.
Why do you need to explicitly remove the self?
Yeah, because no, because when you write an instance, I don't put in self. You see, this is here when I make an instance. When I make an instance, my first instance I made by hand. This one, yeah? So I don't say self. If I put self here as a first argument, I get an exception. Because this is, I call it on the init. The init has a self already. The init is not the constructor. The new is the constructor. There's a dando new, which I never ever remember implementing a new. It's very rare that you need a new. The new is a real constructor that returns something. The self never ever should return anything because the init just initializes. Very often it's called the constructor, which is technically not correct because new constructor is making the instance. The new makes the instance, and the init fills it with initial values. And 99.9% of the time, you just want to fill it with initial values. The new is used for, the only thing is like if you have the singleton pattern, if anybody knows what singleton is, then the new is the good thing. But that is the only application I know of that you need a new. There might be some others which I don't. So, and then the self is part of the signature, but when I use it here, I get an exception that it doesn't take a parameter self. That's why I have to strip the self out. Yeah? So this is something I got an exception that the self is not allowed, and I moved it otherwise. Yeah, you don't think about it usually. But it's very easy in Python because you always get an exception that explains what's going wrong. Another question?
Yeah, so I think the way you've shown things, whenever a class is inheriting, it doesn't need an init, or it shouldn't have an init?
It depends. Depends. So if you have an init, then it will use this one. If not, the init is not special in this case. The inheritance works the same. It goes up the method resolution order. If my class doesn't have the init, it goes to the parent class and takes it from there. And it depends what you want. For all our samples, we didn't override the init because we didn't do anything different. But you can also use super. That's typically what you do. You get something, you do something in addition, and then you typically use super, call the parent init, and then do whatever extra you want. So you can only do extra, you cannot do less. Because when you call a function is one thing, you cannot take things out of the function, but you can do something before or after the init if you want to. Yeah, like you could check values to say, okay, the value that comes in should be in the limit, and I can, if it don't like it, I raise exception, then I just hand the value to the init and don't do the work, for instance. Yeah. So init is exactly the same if it's a normal method or init in terms of inheritance, exactly the same behavior. Good. Okay, let's do a short exercise. I hope it works. So I haven't really rehearsed the exercise because I don't know how to rehearse an exercise. Actually, I haven't rehearsed anything yet. It's a pretty new tutorial here, but so far we are kind of in my anticipated time plan. Let's do an exercise. So if you go to the PDF, there's a description of the exercise. So if you turn on the table of content, then you can go to the object-oriented solution exercise here. And we have an example of, so this is, so we do this, it's called height. So we have this here. Do we have it? I hope I have it. Otherwise I need to upload it and we do the exercise later. Oh. So do we have this? Height. But it should be in there. So the height, why is it not in there? It should be in there, so that the height is there, isn't it? The person's there. Yeah, so we have a person, and we have this heights file. We have a read data and a cut, and I don't have it here. So I need to quickly upload this one, so that this works. So give me a second. So we want to do exercise now. You can read through already, so be following the situations. I need to upload this quickly, and then I give you this thing. It will take me a minute. So we have an existing solution. And we want to modify this. And now nothing works when I'm here. And we want to modify it. And I have a very simple one. We have a CSV file we read in, and I would like to re-implement this procedural solution with object-oriented solution. So we just read in a CSV file, which I gave you, but for some reason the code didn't end up, but it should because I referenced it, and my automatic somehow didn't do it, but I can. Exercises, okay. Okay, I found it. So we have this existing solution, and we would like to modify it and turn it into object-oriented solution. And this is a bit smaller example, but very similar. And now you should try to do this and work on it, and but I need to concentrate on uploading. Data, download, okay. So something always goes wrong, but now we have it. Yeah. No. Okay, so I uploaded. If you need a second, it will be uploaded, and they need to download this zip file again, and I copy it over into my tutorial. So I didn't even realize that's not there. Something always goes wrong when you do something like this, and for some reason this doesn't show up. So if now I know why this didn't work because the resolution is totally different and screws everything up what I'm seeing here. Okay, now if you re-download the whole thing, if you re-download this file, then you should have the directories data and this height in there. So this is application. So if you re-download, you should find this heights. Yeah, and here we have a read data, which is a very simple one that reads a CSV file, nothing special, and we have a calculation, and this calculation does very simple calculations. So calculates the mean, calculates the shortest person and the tallest person from this data. It's very, very simple. It's a very, very simple application that exists. So it's a module here that you can use, yeah, and this one. So everything is included in the PDF, but I didn't give you the source, which is copying from PDF. It's not going to work. Now you should rewrite this one as exercises. So this is a given one, and I quickly go through and I show you the source code. This is a CSV file we read in. This is a person with a height. This in centimeters, by the way, yeah, so no meters and feet, just one number is easier. And then you read it in, and then you can use this one, and you can display the people here, and then you have this great functions, the mean, which exists already in Python as a statistic mean. You can calculate the mean. You have the shortest person, the tallest person, and so on. So this is the given task, the given source code, and then the task now is to rewrite this one with the following steps. Create a class person, so I gave you already a person, so make a class person that has a name and a height, so instead of the functions. Then make some instances, so this, everything is just a few lines, so it's just the person's very short. Instant heights, make instances of this for all data. Write a function that computes the mean value, yeah, the heights for all persons, and create a child class of person that is comparable. We did this comparable thing, yeah? Last time. And then create instances, and then find out which persons is the smallest. So the mathematics is, everything is in the functions already, just move everything into the class. See if it works. So I haven't tried it out on real people, how fast you can do this. Anybody has a question about the content of this function? That's the instructions in the PDF. That's a PDF, and if you go to exercises, then you find it. So PDF, and this is a section here, 5 on the page 31 down here. So this is the 31 in the document, which translates to 38 here. And if you go to the here and go object-oriented solution, exercises, then you find these instructions. And before here is the explanation of these files. I'm not sure why they are not there, because because they are under exercises. Okay. So I can show you quickly how to use this. Not so big. I think I have to make it a bit smaller. So see anything useful. So let's go to the exercise. Make a new notebook. Exercises. So, and now if you have this directory height there, then if I say, so the tree only works on Unix. If you have a Windows, it doesn't work. So tree height, then you see this is my great package, and I do have the data, and I can say from height import from height dot read data import read data. Yeah, and then I can say my data read data lists. Okay, it's a different name. And then I can say my data equals read data lists, and I say data, and data has a check data is called persons. .csv, and then I have my data that looks like this. Yeah, so displayed now with pretty print. You have the names and that. So if you don't like the pretty print, by the way, Python has a lot of magics. You can turn off the pretty print, and then it looks like this. Yeah, so this is one of these magics to get the display differently. And then you can say from height import calculations, and then you can say calculations dot mean, and you can say data 1 should be the second entry, and then you get the mean value. Yeah, so this would be the second entry in my data, and you have the mean value. So not very difficult in terms of what it's doing, and you can also have the shortest person and the tallest person. Calc shortest person, and you have to put in the names and the values, which would be the data 0 and data 1, on which you should yeah, this would be data 0 and data 1 should work, which could be shortcutted too. Yeah, so if you don't want to write this out, then we can use our star thing. This would be the shortest person, and this would be the tallest person. Yeah, so that's what it's doing, and now the output should be the same, that there's no new logic, so you can reuse the logic, but you reassemble them using a class. And of course, the obvious class would be a person, because we work with persons, so please try to implement a person and methods. I will go through, and if you have questions, I can try to help you. So there's quite a few people though, then yeah? Yeah, the star, so this would be equivalent to, we don't need that, but we can make it shorter. So instead of writing this, here in this case, the star is exactly the same as this. So the star unpacks the sequence because the data is a list, one tuple with 2 entries, and the first is the names, the second one, and I can write it like this. If I use this one, so if it would be have data 0, data 1, data 2, data 3, data 4, data 7, this would be the same. It would take everything, it iterates over it. Very often, like if you say print, so if I have a list, yeah, then when I say print list, it just prints the list. If I want to have the single argument, so say print, list, first entry, list, second entry, list, third entry, and so on. Yeah, entry, and so on. But I can say print, and then I just say star L, and I'm doing the same thing. And in fact, you don't even need a list. You can say print star range 10, and now I feed all the numbers from 0 to 9 separately to the print. This always works. This one take this iterable object apart and feed all these things you would get when you iterate over it as single arguments to the function. Pretty long sentence for this little star, yeah. And this can be useful if you're lazy programmers or good programmers. If you can reduce the work and you still know what you're doing, then do it. Yeah? If you end up with a poor code, then you overdid it a bit, shortening the code. So I will come around. I turn off the mic so I don't disturb you. And then after a few minutes, you see how it's going. Good. Okay. Let's continue with the solutions. I'll show you my solution. This is a PDF. It's a solution. You will get this PDF. I will add it as a zip file. So the first thing, write the class person. That should be pretty straightforward. The class person, you have to have the init, and you have a name and a height. And very typically say self, name equals name, self, height equals height. That will be the first thing. There are not so many different options here, I think, so that's pretty much how it should look like. Create instances. You see, there's a solution with a list comprehension. You can also write a loop. If you don't like list comprehensions, you can always write a loop. This is the shortest one. So you create a person with name and height, and you get name and height by zipping name and height. So this is just how you read in name and height. If you have data, you just say data star, but here explicitly the first column is name, the other one is height. Yeah, so we have persons. Write a function becomes a mean. So this is still a function outside. The mean inside the one class doesn't make sense. You need multiple instances. And then you say mean, and you say, okay, now you access person.height for person and persons, provided that persons is a list of the persons. Yeah. So you can always combine functions with classes. It doesn't mean you have to always everything has to be a class. If a simple function is doing it, use a simple function. If you need more, write a class. So and then you can just apply it and you get your mean, you get the same result. And then make it comparable. So for this one, you need the less than. It doesn't hurt to implement the equal or even more. The less than on here, the thing is, this is a criterion you want to use. The height of the person is what you want to compare. Yeah? You could also compare persons by name. Then you use just the name, the string comparison. Yeah, but here we use the height, and then when you do this, you make comparable persons here, and then you can have this min. And you can use a built-in min function, which works the same as a sort and min. Use the same principle with a key function, so it works exactly the same. If you have a less, then you have a min. There you go. Yeah, you can build in bin, and the user doesn't need to know anything. It's just use. So you use min and you throw in your object and it gives you, or your objects, a list of your objects, or a collection of your objects, and then gives it the same thing. Yeah, and the max, very, very easy solution. Yeah, and then representable, that's a bit more involved. For this one, if you have solved this one, you have to have the wrapper, and here it's up to you to create a nice string. And this one is a bit more work. Yeah, you see this exclamation mark R means use a representation of these objects. That has an advantage. It adds the extra quotes for strings. You don't have to fiddle around with this one. So you say, okay, give me the representation of these attributes. These are objects already, built in Python, whatever, and fill them in. And here, again, I use the class name, so I get the class name. Yeah, and then when you see this, then now a person looks like this. If you have your list in the notebook printed out, something like this comes out. Yeah. Second constructor, so maybe you haven't done this yet. So here you have a class method. You just have put in the class and the person, and then you make a new class and you say person.name, person.height, and take those things and fit it into the init. Yeah. So this might be a small exercise, but it gives you some feeling what you can do. In real world, things get more complex and more lines, but the essence should be the same. The essence should be the same, hopefully. Good. Any questions? Anything didn't work? Any unexpected? So usually when I do a training, we do this together in a Jupyter Hub, and then we can exchange the solutions. Usually we also have more time for exercises, but here we will stay with it. Good. This concludes the first part, that when we have this procedural solution, we move step by step into a more object-oriented solution. Now, we would like to go to a different thing. I have to make this bigger. So, the next one is you do object-oriented analysis. So instead of starting from an existing solution, you start from the problem and you start object-oriented from the beginning on. And there are many different ways of doing this, and you have to analyze your problem and come up with a solution. So starting from scratch. And here I have one approach. There might be different approaches. This is one approach how to do this. So actually, you don't start programming right away. You start writing down things first. So defining the problem is always a good thing. You shouldn't overdo it. You shouldn't specify for months. But writing down a little bit is not too bad. So write down your problem with sentences in a way that somebody else who knows something about the domain can understand. So this somebody else can be yourself. 6 weeks, 6 months down the road, then you totally forgot what you meant. You sentence and state your assumptions. Yeah. Then we analyze the text. And our analysis is like grammar 4th grade, 3rd grade. We just go through and find nouns and verbs and maybe adjectives. Just underline them, take them out. And then out of these, we identify potential classes, and then we try to implement some prototype classes and then refactor our code. So there can be a lot of details, but typically if a simple solution works, then use a simple solution. So now I have my story, and that's the whole thing we just talked about all the time, the electric car thing. Yeah? An electric car travels a given distance with constant speed. It has a battery of a certain size in kilowatt hours. The car starts to travel with 80% charged battery, once the battery, and so on. This is a text, and these are the same assumptions. So they're from the same file, they include the same file in this place. So these are the assumptions we looked at. Write down a narrative, use full sentences, and formulate in a way that if you give somebody else, somebody else would understand what you mean. Then makes a lot of sense because it makes you think. When you have to formulate, it makes you think about it. And this is what I did. So I have these assumptions here, which are our assumptions so far. And then we do the analysis, and you see, I just go through, and now I collect all my nouns, and then I have the verbs that I use, the verbs with 2 here that you can see the verbs. So I have a car or electric car here in this case, and this car travels, there's a start and there's a charge. That's what I took from the text. And there's a lot of other nouns, distance, speed, battery size, travel, and so on. Yeah? There are a lot of nouns here. Not all nouns should become classes typically, not all of them. Only the ones you are interested in. Because we do have an objective with our modeling, and only these most important nouns that are in the center of our objective will become classes. The other ones are just stay normal attributes, just numbers, strings, or lists, or something like this. Yeah, battery charge, yeah? You reach a battery charge, you have a charging station, so if you haven't looked at a charging station at all, you might have a different objective. You want to plan charging stations, you see, you want to have the best distribution of charging stations to minimize travel time and charging time and whatever, and then you might want to have a charging station as a class. Here, the charging station doesn't matter, we just take them as given, as provided. We don't do anything with the charging station, we just drive. Yeah? Charging rate, travel time, and so on. So a lot of these words come here. Most of them won't become classes, typically. But this can be helpful. So this is technically not very difficult. writing a good text that is readable, going through, identifying. So if you want, you can write a script for nouns and verbs, but you cannot do it by hand. Go through and sort them a little bit. There might be more sophisticated techniques. Simple is good as long as it works. Yeah. So and of course the nouns are candidates for classes, and the verbs are candidates for methods. Nouns are something, methods do something. There might be the exception to the rule, and very often in English you can use the same word for a verb and a noun, like some can be the some or to some. So it doesn't work in every language, by the way, but very often it can be two things at the same time with the same word. And then we have this modeling analogy. So I talked about this modeling. So modeling is a representation of the word. And now I looked for a quote. Most of the people say Albert Einstein is a source that the other sources, everything should be made as simple as possible, but not simpler. If you make it too simple, it's wrong. Yeah. So I go to modeling conferences, and there was one theme: all models are wrong, some are useful. So there's always something is not totally correct, but it's good enough for our purpose. Yeah. So if you look in your car and you measure the speed, you don't measure the speed with 20 digits after the period. You don't need this. So why? Yeah. So it's roughly good enough. If it even doesn't have any decimal places, and it's good enough for our purposes. Same here. So don't make it too complicated, but also not simpler. So this is something that's easier said than done, because very often you don't know how this works. So here we state our objective: find the travel time of an electric car considering battery charging, sort multiple cars by travel time. So that's our objective. These objectives might change over time, and then you need to revisit them and reword, or if your assumptions change and so on. Yeah, so. And then I do something. Still, I want to have my thing kind of future-proof, which is not easy. Yeah, so this can lead to over-engineering if you put in a lot of possibilities that never going to happen. But sometimes it might make sense to prepare for some future changes that are very likely. Not easy, but what you have. So you might know this, you ain't going to need it thing, so you might add a lot of things you're never going to use later on, because you have to somehow predict what's going to happen. That's kind of tough. But if you say now it's not very expensive to design it in a way that you can still do it later, you don't stop it. Yeah. So I don't hardwire the gravity as 9.81 to be of the Earth. So just give it a name G, and then I can put the value. That would work on Mars, my equation, because I make it a variable. So that's not very expensive to make it a variable, just then instead of hardwiring the number. Yeah? If I ever use this model on Mars, I don't know, but maybe even better to have the number in a different place than in the code. Yeah, this would be a pretty easy decision. Sometimes it's not so easy. So this is a little bit thinking, has nothing to do with programming, it's just general problem solving. And if the problem is big, usually you don't do it in one day. Usually I wake up in the morning and I was thinking hard and nothing came out. Wake in the morning, so easy. Very obvious, yeah. So this is something you need to do. And now we see, consider the aging of the battery. So nowadays, batteries age. Yeah? You might have also from your laptop in the beginning. After a few years, you might not last that long anymore. These types of batteries, they have some effect, memory effect, and what kind of thing. Yeah. So they lose some capacity over time, and then say, okay, maybe we would like to take this into consideration. Maybe in 10 years there will be totally no batteries, there's no issue anymore. But who knows? I don't know. But say, okay, this is what we want. So then this would kind of say, okay, now we have to do a little bit more about the battery. Why not make the battery our own class? Before we just had a car and the battery was a part of the car. Now we can make the battery our own class. This would be a little bit different here. If you do it in a way it doesn't hurt, it's okay. Yeah? So it doesn't make it more complicated, it doesn't produce a lot of more work, then it's okay. If you don't need this thing, then it doesn't hurt too much. Yeah. So how likely? No. So the other things, so now we keep the time and distance information. For instance, you could class it that stores those information so you can check what happened. Actually, we need it for the printing, so that's that where I changed it. So the interesting here. So now we design our class, and here this is a decision now. You think about it longer, so we have our eCar we had before. So now we are not unbiased. We implemented it before. We don't really fresh, but it's okay. And we have a battery. And so the battery will also become a class. And then here I have the other nouns become attributes of this class. It's pretty much written in the text. Of course, the model brand is all attributes of the eCar. We had this before. It's not that new. And then these verbs to drive, to get to reach. Maybe not all the verbs will become methods, but drive and we had already. And so the charge is gone. The charge went to the battery. Yeah, when you say you charge a car, it's actually not correct. You charge the battery of the car if you want. Yeah. And then we have the battery, and the battery has attributes, the size, the charge, which is the verb here. So I always use charge as the verb, charging, as a noun, the charge, and charging as a kind of a noun, charging rate. How this is a process, and this is the current state. Yeah. So, and then to charge, to charge several times, and then the nouns we have not used charging station, travel time, and travel we haven't used as a travel time we used before? No, so I haven't used it here. So they are left over. Maybe we can consider some later. So this is some thinking, and depending how complex your problem is, and also this could also be a tool if you need to talk to other people that are from the domain but not programmers. That's a good thing because they can write text and they can sort nouns and things, so they can help you here to identify what's important. Because there's not a single line of Python involved yet. Just general thinking. Good. So now we have the battery. Now let's look at these things. I make a new notebook, as always. And we call this analysis. Analysis. This way. So analysis. So we analyze everything here. And again, I seed it into my eCars thing. And I need to check this. Yeah, so, and I called this first. So, object and first. And here, I'm reusing the code for before. So, this wouldn't happen, but I don't want to re-implement the same thing. And also, I made it deliberately that looks very similar to the other one because we have this prior experience, right? But see now I have an eCar, and I do have, which looks very similar, and I have a battery. So the battery is new. The eCar is very similar. The battery is new, and of course, everything that has to do with charging moves to the battery. That's my new thing. Yeah. Otherwise, the functionality is exactly the same as before, but the layout is different. Now I have two classes, two own types of objects. And of course, now the battery, that's a battery. The battery has, check what I've written here. The battery has some new features, has a size, a current charge, a charging rate, and the effective charging rate. Which I can provide here. So the size current is given, and here the effective charging rate can be none, and if it's none, I take the same as a charging rate. Yeah? So we have this new, or I can say this is effective. The charging rate is a charging rate that the producer puts in this, writes down and say this is a charging rate, but when this one could be say, okay, after 2 years the charging rate is reduced by 5% or something like this. Yeah, that would be an effective one. You could This is the first thing. And then you see, of course, the effective charging rate needs to be smaller than the charging rate. If it's bigger than the charging rate, then I don't like it and raise an exception, for instance. So an error check, which could be helpful, I put in, and now I have some new functionality, because that's my definition. The effective charging rate can only be 100%, not 110%. Yeah, cannot be more than everything. And now the charge moved here. The charge moved here. Now this is the same calculation we did before, the charging rate. But what I do now, I have the current charge. This is new. We didn't have this. This is a state. So now this one knows the current charge. So I can always ask the current charge. Of course, we didn't have this before. We didn't care about. We just drove to the next charging. But now we have this information. And also added a new thing, discharge. Discharge, because now I have this current charge to keep track of it at discharge, and that's take this charging amount off from my charge. Yeah, this is something new, and this I might need some improvements. So I have to be. But I don't check here theoretically. I don't check that I have enough. So I can discharge to minus 20% here if I wanted to. Nobody's going to check it here. Check somewhere else, but that might be a good place to say you can only discharge to 0, or even say you get a warning if you discharge below 20 or below 10% or something. Yeah. So usually you shouldn't go below 10 there. So if you drive a car that's blinking at your red, you should charge now. Yeah. So that's something you can do. So now when you execute the whole thing, it will give you the same output as before, but we distributed our content over multiple classes, in this case 2 classes, and we made the battery our own thing and put more stress in the battery, which makes sense because that's a new element of electric cars is a battery, and if you have a good battery, usually you have a good car most of the time. So probably makes sense also to have the battery as our own thing. We have more information about the battery, and this is a result of our design going through and identifying the objects that are important, and looking at them and coming up with this new design. Otherwise, if you look at the content of the mathematics, there's not much new, just they're a little bit differently arranged. And everything that concerns charging went to the battery, and everything that concerns driving stayed in the car. Yeah? So we didn't look at the engine at all, because the electric engine didn't appear at us, wasn't even mentioned. Of course, it's there, but for our purpose, we don't have to make it our own class or anything. Yeah? If you design electric engines, it might be very different, then you might be much more interested in electric engines. Fortunately, electric engines are technically much simpler than a combustion engine. So pretty much more robust. We don't have all these moving parts. Good. So this is a difference. So I have now take it apart. If you look at this one, that looks very similar. It looks very similar. I have one small change. So because now something moved to the battery. So before we in our object-oriented solution. So if you go back here, I clean it a little bit. You see, here we have this the battery size. The battery size was a property of the car. Now we have a battery that has a property size, yeah, and moved away. But I want to use the same interface, and I did a small trick. Just close this a little bit. I'm getting lost here. Yeah, that must be it. No? Did I close the wrong one? Wrong one. Analysis. No, analysis. Yeah. Good. So the battery size. I still put the battery size in. I keep the same argument, but you see, the battery size is not stored here, but I give the battery size to battery. But in order, I would like to have a property battery size of the car also, but I want to store the information size only once. And to do this, I use this thing. Anybody knows what this thing is? A property. You make sure what?
It makes it so you can only read, so you can read that.
Yeah, you cannot say that. That's a side effect. So a property is very often sometimes called a computed attribute. In the background, this is an application of descriptors, but let's look at a property. If I have a class, the typical example of a property is a class square, yeah, and then you have an init and you get a side. So a square is a rectangle where both sides have the same side, and I say self-side is side. And then I define a property, and I call this area. Define area and self, and I just return self side squared. Yeah, and now I can make a square instance, and to say, okay, this is now the side of 5, and now I can access area, and this gives me back. So this is not a method anymore. Usually a method, if it's like this, you have to put the parentheses. Here you don't put any parentheses, and it is computed in the background. As soon as you access this attribute, Python is invoking a pretty complicated process, which we don't have to be concerned about how it works in detail, and it returns this return value of this area. That's called the computed attribute. This can be useful if you start out with a constant value and you use it, and then later on you decide it has to be a method to compute this value because it's not constant anymore. Then you can use a property, so the API, so the outside view of this attribute looks the same. If somebody accesses this attribute as a constant value, you can use access same. There's no difference, but in the background something else happens. Yeah, so you can keep the interface from outside. That's when used. That's very useful. And that's what I did here. So now I just delegate. I say there still looks like, from outside it looks like my car still has a property battery size, but actually it just delegates to the battery and gets the size from the battery. Yeah. So that means the size is only stored inside the battery, and the car asks the battery, what's your size? Instead of storing this value. You store the value twice and you change it, and you have two different battery sizes. That's not going to work. So this can work. Of course, this generates a coupling between the car and the battery, but there's a coupling anyway, because the battery is only inside the car. We are only concerned about car batteries. If you recycle things, you might use car batteries later for something else, but that's not in our concern here. The car only comes inside. The battery only is inside the car, so the coupling is kind of okay. Yeah, so those things you can think about if it's always the case and so on. And now this property from outside looks exactly the same. I can use the same functions to work with my car, but inside I have a class battery, which now later I could have an algorithm and say, okay, introduce a time, and the battery is aging over time. So the time is still missing. The time thing. Yeah, well, the time, and also I could do statistics, how often is the battery charged and discharged, to what degree, because this also influences the lifetime of the battery. If you discharge very low all the time, then probably you reduce the battery capacity very quickly. Okay. You might know this if you don't take care of the battery and just do it, then this is very similar. Depends very much on technology. If soon there will be new technologies that use different kind of physics, then they might not be that applicable anymore. Yeah, but this is a pretty code, but this is just the translation. The main thing goes in the analysis first. What I want to achieve, what classes do I need? How could it develop in the future? Yeah, but this can lead to a lot of things you implement you never ever going to need. But in this case, it's not so much more complicated. It's doing the same thing, only that I moved something into the class battery here that takes over a few of these things I'm doing. Okay, this is my take on analyzing your problem, coming up with a solution. Do you have any questions about this kind of strategy here? Yeah.
So, and then I think you implemented the LP, so you've got comparability in the main class now. Would you do the representation as well on
I didn't understand this question. Can you repeat?
So in your new e-card class,
Yeah.
I think you put the comparability, the less than, in that class directly, not inherited. Is that right?
Yeah, you don't have to put it this. The inheritance here is actually more a tool for me to focus on the thing. So in the real world life, I wouldn't do all these inheritance steps. This is just for didactical reasons that you can better understand. Probably I would put all these special methods in one class. Yeah? So the inheritance here is used just because we want to focus on this new feature. Everything else is the same, only this thing changes. And to explain this inheritance, it's good. I do the same thing. I teach a course about GUI design and graphical user interfaces, and they do the same thing. I want to start with a base example and then inherit and add more thing, add more thing, more thing. In real world, it would be only one class, potentially. Yeah? But to focus on the new thing, otherwise it got get bigger. And it's just it's the same thing. It's just for didactical reasons. Yeah. So most of the inheritance we used here is just to make it easier to digest in this thing. Good. Any more questions? Okay. I do have an exercise. I only have 15 minutes, so probably not going to make it in full. But it's also something more or less to take home. So this would be the exercise. Maybe we can get started. So I have a big appendix where I explain how, by the way, there's the data preparation, where I get the data from, and then how to make the graph. So if you're interested in the graph, I have a long thing about the graph, but just not so important. So this would be the exercise. Here, maybe you can choose a small problem from your domain, and then go about, write your user story, state your assumptions, yeah, and then do this. The following would be, I have an example here about computers, virtual machines, and something like this. Where if you don't have an example, this should be still general enough for programmers that you know what a virtual machine is, and you can go to the cloud and spin up some machines without a lot of details, and use a Docker container, which is just, even if you don't use Docker, this is just a thing where you can install everything with one thing, so to speak, and everything runs immediately. And then there are some assumptions here. You see a long list of assumptions that we have. So this is the given task. Alternatively, come up with your own task and analyze your own task. Analyze your own task. Good. And then go through. The solutions shouldn't appear here, but the solution is not shown. Explicitly write down what the program should do, identify classes, methods, and attributes. So no implementation yet, actually. Yeah, you can some implementations, but you can just use stubs. So the methods don't do anything. You just give method names. So you come up with class names and method names, but don't put any implementation. That would be difficult anyway. So the solution is still clicking here through. Okay, this would be the exercise we should do, but let's go back to my presentation. Yeah, so advantages. So I wrap up the presentation, then we do the exercise because it's a little bit open-ended. Advantages of this object-oriented programming. So if you want, you can say you can have a higher level of abstraction, because now you can use better words from your domain. Those class names, method names might be better than function names. you can use analogy of modeling of real-world objects with object representations, real-world things. Inheritance can be good for code reuse. We've seen this here for these examples. Yeah. It's very established, so object orientation originates in the 70s, 80s. Smalltalk in the 80s was the first one, so it's not a very new thing. It's been around for a while. There's also a lot of criticism about object orientation. And the answer on Python is you can always combine object orientation. You can only do part of your program in this way and the rest the other way. Totally fine. Yeah, and you can have more extensible design if you do it in the correct way. Good. Disadvantages: inheritance creates dependencies. I told you when you inherit, you get everything from your parent. You have to turn something off. If you don't want it, you have to turn it off explicitly. Yeah. It might lead to a little bit of this over-engineering thing, so you add more things. So I still remember I took part in one of those small programming competitions. You take a piece of text and get some references out. And I was inspired by other solution, but the Python solution was 8 lines or so, finished. And this guy came with a Java solution, 250 lines. And he had the interface here, an interface there, or something there. So he solved a lot of problems they didn't ask for. Yeah? So this could be useful, maybe, potentially, but it's a lot of extra work that may not be needed later on. Yeah? And if you do it wrong, it can make things more complex, but all of a sudden you have all kinds of connections between objects you don't want. Yeah? So if you, actually, in Python you have pylint has pyreverse inside, so you can take your classes and it creates a class diagram, a UML class diagram. Usually it's the other way around. You use this. There's a lot of tools, UML, for modeling range, so you can model your objects graphically, and then from this they generate code stubs. In Python you can program your classes and then generate these files, and then you see that who's inheriting from whom and how it looks like graphically. And that can be useful if everything is like totally, everybody's connected, everything this might be too much. You want to have a clean hierarchy. Yeah? So there are some tools out there that help you to visualize things, and maybe they can be useful not to make your program too complicated. Pylint, and I think the command is pyreverse. So when you install pylint and it creates a dot file, you need to install this graph to visualize the dot file. Yeah? There might be other tools. That's a tool I know. So what to do? From my perspective, in Python you can always use multiple programming paradigms. So you just write functions, use classes, use functional programming. The list comprehension we did is you might put them into the box functional programming. Yeah? So iterators might belong to the box functional programming. Write functions can be, if there's enough on the small write functions, you don't have to always say, I have to write the class. No need. Yeah? Important is a function gets input arguments and returns an output and shouldn't change the world outside. If you need to change the world outside, then you should consider a class where you put everything into a class and you have the self dot, and everything under self could be your local world you change between the methods. That's my recommendation. Yeah? So use functional features if you like, and everything that looks like a pipeline. You have this step, you move it to the next, you move it to the next, to the move to the next. This is typically something that you can use functional features in a better way. Yeah? So different tasks are more suitable for different paradigms, and you can combine them in your way. This is a pretty broad thing, but that's my experience. And we've seen here this electric car has a state that everything changes, so it makes sense. It makes sense because something changes over time, and you want to keep track what's going on, and a lot of things are connected. Then having an object is pretty good. If you just process something and you have like on this really a pipeline, then maybe a functional approach would be better. Good. Any more questions? So the exercise is still outstanding, but this is a kind of an open-ended exercise. You see, it's a pretty general one. I gave you some idea. I have a solution for this exercise I wrote you. I will add this solution to the zip file, also in my notebooks. Then you have everything in the zip file. So if you feel like you can start now with the exercise, I will stick around. You can also ask me more questions either now or later. I will be around through the sprints, so if you can catch me somewhere on the hallway, then you can always talk to me about these things. I will stay here for a little bit longer for questions if you want to come. Otherwise, I thank you very much for your being here. You can start the exercises now, or go have lunch, or come to me and ask questions. Thank you very much.